Good morning, friends. Today we are going to take a different session from critical appraisal. It's also critically looking at a topic. It's linked to systematic reviews, which we often do in our CEU, though we try to look at different study designs. Today's topic is looking at the conclusiveness of a systematic review of evidence. So, conclusiveness is the key word. So, we often think that systematic review is the best evidence to make decisions. If the systematic review is unequivocal, we can make decisions, meaning it is definitely showing something is either good, bad or doesn't work, that is unequivocal, we can make confident decisions. If the evidence base is insufficient, meaning the systematic review finally is not able to conclude one way or the other, we say the evidence is inconclusive from the systematic review. It is not the fault of the systematic review, maybe the studies are of poor quality or small numbers to make any conclusive evidence. This concept is called the conclusiveness of a systematic review. Some people like the word inconclusive as the opposite of conclusive. Some people like the word questionable, doubtful, unconvincing, disputable, indefinite, ambiguous or refutable. So, there are other words beside the word conclusiveness or lack of conclusiveness, inconclusive or other words. So, in a systematic review, we do usually quantitative methods to combine studies. Suppose we say at the end of the study that there are many patients who are from children, many studies from children, some from adults, some from a geriatric population. We say we do not want to combine them mathematically, we will just describe the different results. So, it could be a narrative review or we can combine them mathematically with the meta-analysis. What we also learnt every Saturday is risk of bias. Risk of bias is the inbuilt validity of each study and that varies depending on the study design. Risk of bias for case control, cross-sectional studies, RCTs. So, there is a risk of bias for each one. Once we have done the risk of bias, we do what is called grade. Again, some people use grade, some people use another methodology to look at the overall evidence, the quality of the evidence in a systematic review. And then we must look at the comprehensiveness of the or applicability of the included studies. And then you finally say that I am confident in my findings or not confident. So, this is just a joke that sometimes we decide that this is the result we want to find and all studies which do not give us a result we want, we call them inconclusive. So, it will be a bit careful that sometimes we can manipulate results to get the results we want. So, going back, what is conclusiveness? It is a certainty or confidence in our findings. Another way to put it is the likelihood that a systematic review conclusion will change if new studies are added. In other words, we have a systematic review showing that treatment A is better than B, but we are a bit worried. Suppose a new study comes, will this whole review evidence change? Why should we look at that? Well, the evidence may say that what was looking like benefit may look at no benefit, or what was benefit may now turn to harm. For people who are researchers, when they look at a systematic review and say it is conclusive, they will say no need to do any more studies, because the systematic review is conclusive. There is no need to add any more studies because they will be redundant. If you find, if you are a policy maker, researcher, funder, an inconclusive systematic review, it is an opportunity for new studies, because then that will reduce the uncertainty of the systematic review. Guideline developers, if they have a conclusive systematic review or reviews, they can make confident recommendations. On the other hand, if they find their systematic reviews are all inconclusive, their confidence in their recommendations comes down. So, this is the philosophy of what is called conclusiveness. Now, very often in medicine we do not have conclusive evidence before we make guidelines, but we have to make guidelines nonetheless. So, we should not land up in a situation where we make some decision and only after we make a wrong decision we realize, oops, the decision we took was a wrong decision. So, that is just a little bit of humor about conclusiveness. So, I'll stop here. Any questions? This is the basic funda of what is conclusiveness. So, for researchers, if there are a conclusive systematic review, don't do any more studies. If there is an inconclusive systematic review, do some more well conducted large studies. And for guideline developers, if the review is conclusive, you can make confident recommendations. Whereas if the reviews are inconclusive, we are less confident in our recommendations, and we should make these ante-mortem, not post-mortem. The next point is that statistical significance is not equal to conclusiveness. Now, very often we have learnt now in various Saturday sessions that we have an effect estimate, which is the odds ratio or the relative risk or risk difference, and its confidence interval. And we look at statistical significance, meaning if the confidence interval doesn't touch 1, then we say that the likelihood estimate excludes the possibility of no difference. And very often we mistake statistical significance for clinical significance. And if you listen to Reba's talk on grade, we now know that statistical significance is not equal to clinical significance, and conclusiveness is really about clinical significance. It is not about statistical significance. So, if you ask somebody, yeah, this systematic review showed, for example, a recent Cochrane systematic review showed that, maybe we should review that, prostate specific antigen screening reduces mortality, but it's 2 out of 1000, and 15 or 16 people will unnecessarily undergo a lot of tests. So, you can say yes, the p value was significant, the odds ratio did not cross 1, but is that difference clinically meaningful? So, if the old person was to ask his doctor, does PSA work as a screening test, it depends on what you mean by does it and work. So, you have to be careful about this. What is the interpretation of conclusiveness? It is really clinical significance. Now, we come to something again which was taken earlier by Reba during her grade talks, optimum information size in a systematic review. So, even in a systematic review, we need to have a minimum number of people in all the studies put together to conclude if one treatment is better than something else, or this is really a good prognosis study, or even this is a good case control systematic review. Do you have enough number of people together in all the studies put together? Now, why should we look at a sample size? In effect, it's like a sample size calculation in systematic review. False positive is concluding that treatment A is better than B when it's not. False negative is actually treatment A is better, but the systematic review now concluded it's not better. So, it's similar to a traditional sample size calculation in a single trial. So, we have an effect size. What is the difference we are trying to estimate? We know the control event rate. So, what is the event rate in people who do not have the new treatment? We specify an alpha error, which is a false positive error. We specify a beta error, which is also false negative, which is the inverse or the ulta of power. And in a systematic review, there is one more concept to do sample size, which is we must account for heterogeneity when we are doing sample size calculation, which we do not do in a single study. We do not look at heterogeneity. And if anybody is interested in reading more about this, there is a nice, if you just Google this, Cochrane prospective approaches to accumulating evidence, it talks more about these kind of optimum information size. So, as you can see, what I have been alluding so far is, it is really about should we add new studies or should we not add new studies to our systematic review. So, addition of new studies can change your conclusion in several ways. If the new studies also say A is better than B, it has increased our confidence that A is better than B. If you add more studies, you know that the confidence interval will narrow or widen? Narrow. So, the confidence bounds become tighter, tighter means narrower, and we are more happy. Sometimes even if you are just doing a narrative review, like I told you earlier, one study on neonates, one on adults, one on geriatrics, we decided that we can't compare them all together. We do not do a meta-analysis, we just describe each study. Even in that situation, one more study which shows the same thing adds to our confidence. On the other hand, A is better than B may suddenly change to A is not better than B. It may also go the other way. Suddenly you may find that adding one more study suddenly concludes that treatment B is better than A. So, that is the effect of why we should look and decide whether we need no studies or we don't need new studies. So when everybody says, I believe that this treatment is great, then somebody will say, slow down, the evidence isn't complete. So even some people say the new study should be so big and so big, but there's a concept of sensitive data. Even a small study may be able to change your confidence in the final systematic review estimate. So just being sensitive, small amount of data itself can change sometimes, and I'll talk about the methodology and then you'll understand what I mean by sensitive data. Now this is a randomized control study taken from a dental, about people with having dental surgery for some jaw abnormality. The first study was done by Osbeck in 1998, and he found, and this is the line of no difference, the difference between two surgeries. So this is 0, not relative risk of 1, because we are looking at the difference. The null effect is 0, and the null effect in the first study was 1.97, suggesting the new intervention was good. The second was 2, but the second study is not just the second study alone, it is the data of Osbeck plus Jenna. This is called cumulative meta-analysis. The third study was Jenna part 2, hopefully it was a different number of patients. This was 2013, and when you added it, it came to 1.98. So if you had stopped the review here, you will say yes, the treatment appears to be highly effective. But then there was Ulusoy. When you added Ulusoy, suddenly you say, oh, the effect estimate has come down and the confidence interval has become wide. Similarly, when you added Ali and Baumbeck, the change happened more. Of course, you may say the mean difference is there, but suddenly the mean difference started coming towards the null and the confidence interval started to widen. So therefore, you should always not say that, we have 4 large studies, let us stop. There may be many small studies which having lower effect, which in the end will lower your point estimate and may widen the confidence interval, and thereby lowering your confidence in the systematic review or the conclusiveness of the systematic review. Now in Cochrane, now they say that you done a Cochrane review and you find that 10 ongoing studies are there. So you don't have to wait for them, you are already ready, like okay, you contact the author, you take the date, the study design is already correct, you have your review topic, you have your PICO. When the new data comes, quickly you add it on. So you are going to add on new studies to your existing systematic review. So if you are interested, you can read about this Cochrane evidence platform and pipeline, and it is taken from the Cochrane handbook, which is free to read. So chapter 22 is the place where you can read about this planned meta-analysis. Now I just wanted to put up there because much of my talk is based on this particular paper by Ban and Lund and colleagues. It was published in March 2026 in the Annals of Internal Medicine. It says determining the conclusiveness of a systematic review evidence. So very often what I am going to talk about will sound like take an article and then make mincemeat of it and say it's useless. So very often people think critical appraisal is taking some article and then saying that it is stupid, it's saying it's useless. That's not the idea of this Saturday sessions. We just want to teach people. So I'm going to teach you that conclusiveness of a systematic review has various approaches, and I hope that I'll tell you when you must use which approach, right? So this I studied BSc zoology, and then you can classify every animal into vertebrate, non-vertebrate, mammals, non-mammals. Like that, people in statistics love classifications. So conclusiveness of a meta-analysis, there are 3 broad headings. One are called mathematical approaches to a meta-analysis. The second is mathematical approach to cumulative meta-analysis. And the third are non-mathematical approaches, which is really grade and children of grade. Children of grade, I am making fun. It's like, if Cochrane uses grade, somebody else will use Ottawa and somebody else will use, Joanna Briggs' method of looking at conclusiveness. So these are non-mathematical approaches. I will spend little time on this. I am going to spend more time on mathematical approaches to meta-analysis, mathematical approaches to cumulative meta-analysis, which I have explained are 2 different things. And these are all about, the topic is conclusiveness of meta-analysis. Now these authors found 29 different methods for mathematical approaches. So I told you the mathematical approaches, there are 29 approaches, and we can't possibly go through 29 approaches. but they have classified them into 9 groups. One is called safe number, Bayesian methods, Barrowman's N, simulation based methods, conditional power, fragility index, extended funnel plots, cumulative meta-analysis and machine learning models. I am going to spend more time on the first 2-3 methods. So, the first 2-3 I told you are the fail-safe number, Bayesian method and Barrowman's N method. Now, some people will get, for 17 plus 7 is obviously 24, but some people will put a factorial and put this and that and try to use algebra to sort it out, annotations. But this fail-safe number is actually a really simple concept. This is a beautiful article written by Rosenthal in 1979, published in the APA Psychological Bulletin. It's a simple concept. So, imagine that you have actually 100 studies and your search strategy found 5 studies, and all those studies were actually the type 1 errors, meaning those 5 studies concluded that treatment A is better than B. Actually, they are just by chance finding out A is better than B, they are all type 1. The remaining 95 studies your search did not find out. Where are they? They kept safely in a drawer. So, this is called, he called it the file drawer problem. Drawer means a desk with drawers, not underwear drawer. Okay, I am just making fun to wake everybody up. So, the file drawer problem is there are a large number of inconclusive studies, meaning randomized control studies which do not show that treatment A is better than B, which are hiding somewhere. You only found the 5 studies which showed A is better than B, but those probably are just type 1 errors. So, this is, he called this as the file drawer problem, right. So, that is the basic concept of this whole issue called fail-safe number. So, what is the fail-safe number? The potential number of potentially unpublished studies with no or negative effect. So, usually if the study is positive, you can get it published, but if the study shows that A is equal to B or B is better than A, then nobody will publish that. If those kind of unpublished studies exist, they will shift a meta-analysis from significant to non-significant. So, that is the most important thing. You found 5 studies which are highly significant and I am very happy. How many studies should I add which are non-significant, which will change the overall meta-analysis to non-significant? That is called fail-safe number, and if the n number of trials, let us say the number of trials you found is 5, 25, 5 into 5, 25 plus 10, 35. So, if the fail-safe number is more than 35, you will say it is okay, but less than 35, you will say, oh, there may be some worthwhile studies out there. Anyway, that is just a concept, is the fail-safe number. How many studies which are negative, if I add, will change the results to non-significant. Now, simulation is just simulation. I do not have data, but I can simulate data from other studies. I do not have another study, I can imagine that there are other studies. What will happen if I add some more studies? So, I am not going to go into the methodology. If anybody is interested, we can talk about that. So, there are simulation based power methods. Then you can do for cluster randomized studies, for genetic studies, for diagnostic studies, also for meta regression. So, regression analysis within a systematic review is called meta regression. So, basically it is like you have one study and you simulate many studies, it sounds a bit silly in concept, but technically one can do this, and that is called simulation based power methods. Conditional power methods, what are they? And there is a extension for network meta-analysis. Basically, if you look at a large randomized control study, let us say 10,000 people, and halfway through at 5,000 you stop and say like, okay, how am I doing so far? Like, am I showing that A is better than B? Am I showing both are not at all different, or maybe suddenly I found out B is better than A? And we know that power is ability to find a difference if it truly exists. So, halfway through one can stop, and there are many stopping rules. Should I stop now? Should I not stop now? One of the things which people do is called conditional power. How much power do I have to find a difference at this halfway mark? It is not the power at the end of the study, it is somewhere in between. You can choose when you want to stop. That is called conditional power in a single study. Similarly, one can do conditional power in a systematic review of many studies and say, do I have enough power to now conclude truly that I have found out a difference? So, that is called conditional power, and People hate this conditional. Conditional is like Bayesian thought. If A is present, then what will happen to B? Or given this prior knowledge, what will happen? So many people do not like this conditional idea at all, because it's probability, it's conditional probability. So it's a little bit of a thought experiment. Anyway, so that's about conditional power. So these are two methods, simulation based and conditional power methods. Now I want to talk about two other things. There are nice references to the next two slides. One is this, when is a further clinical trial justified, published in the BMJ by Ferreira and Sutton and colleagues. And the second one is this, statistics in brief, the fragility index by Stern and Poran et al. So these two concepts I want to spend some time explaining, fragility index and extended funnel plots. So fragility index, let me just give you an example. Okay, fragility index divided by the number of subjects in all the studies gives you a number called fragility quotient. So fragility index is for studies which have shown a positive result. I want to neutralize it. Reverse fragility index is studies which have shown negative result. How many positive studies should I find to now make it a positive result? So just a concept, fragility and reverse fragility, where you start off from. Fragility index starts off with positive studies. How many negative studies should I add to? Not studies. So let's have a look at this picture. There are 30 people in a control group. There are 30 people in the treatment arm. Which arm has more cure rate? Black is cure. Treatment group. See, they can say that this is the number not cured here. Only few people are not cured. 3 people are not cured here. P value is significant. Now I do the fragility index. What is the change between this and this, Nishi? Between this group and this. This is the simulation. 1 less. From only 3 not cured, I made it 4 not cured, or just 1 difference. This one, same. What happened to the P value? Changed. So what's the fragility index? 1. You can see the results are highly fragile. Even if one person's results change, the whole story changes. So this is called fragility index, and if you, that index divided by the total number of subjects in the review is called fragility quotient. Reverse fragility index is you start off with nil studies and you want to do the other way around. Okay, so that's that. Do you remember this picture from a little while ago? This is the no effect line. This is crossing this side. This is harm, this is benefit. So this is clearly no effect. This also is no statistical effect. This has a statistical effect, meaning P is less than 0.05, but this is the minimum clinically important difference. Simple English, smallest worthwhile effect. So this, does it cross the smallest worthwhile effect? No. This one, it's somewhere there, it's unclear. This is maybe but may not be, and this is definitely crossing. So this is how you do this meta-analysis to decide, hey, if I add more studies, what do you hope? If you add more studies, what do you hope? The studies, the systematic review which was here, if you add more studies, you hope to come here. So for publication bias, remember the plot? Anybody remembers what plot it is? Very good, funnel plot. So I am just showing you one half of the funnel plot. This funnel plot curve should come like that. Okay, I am not showing the rest of the funnel plot. I am just showing you one arm of the funnel plot. What is this line here? No effect. Let's say odds ratio of 1. That's the same line here. What is this line? Minimum clinically important difference, or the smallest worthwhile effect. When you add colors to it's called contoured plot. Now this is, and the y-axis is standard error. Also it can be, it's equal to the sample size. If I add one large study to the existing systematic review, large because standard error of 0 means very large studies, it doesn't change the overall effect. If I add another large study, slightly less effect, it doesn't change. So 1, 2, 3, 4, 5, 6. When I add the 8th study, only then the effect changes to clinically meaningful effect. So this is called extended funnel plot, where it's the same kind of concept. In a funnel plot, you can see if I add studies, large studies with a wide confidence interval, small studies with narrow confidence interval, how many studies should I add before this estimate shifts into the boundary of, it's the same, it's a different visualization of the same thing. So this is called extended funnel plot. Now we go on to the next one called cumulative meta-analysis, and you can do also prediction and learning models. Now let me give an example. For people with heart disease, there are two types of, the most popular drug is this called everolimus. You can have a metal stent with everolimus, or you can have a polymeric stent with everolimus, also called bioresorbable stent. So on the x-axis is time, on the y-axis are the various studies. For example, Absorb 2 was done in 2011 to 2014, Overbio, Absorb. So you can see that Absorb 4 was done between 2014 and 2017. It was initially given for trials in 2011. The government said you can start doing, government, probably US government said you can start doing trials. After so many studies are over, by 2017, between 2016, maybe December 2016, FDA gave approval for the polymeric everolimus bioresorbable stent. Strangely, about a year later, the stent was withdrawn. Why? So this is a cumulative meta-analysis. That means Absorb 2 is the first study, Overbio is the second study, but this is harm, bioresorbable stent blocking. It should not block. The whole idea is to keep the artery open. Thrombosis means the artery is blocked. So the point estimate is here, but the confidence interval is crossing 1. When we added Overbio, what happened? It didn't change. When we added Absorb, it moved towards the null. Trophy, it came here. So by the end of the first year of follow, about a year later, they were still saying that, hello, there's a possibility that this new stent may cause harm. What happened by the 2016 started, FDA approved in July 2016. When they started adding the new studies which came after 2016, is there any doubt? Confidence interval, these are not single studies. This data is all these studies up to here. Absorb 2 added to the previous data is this number, cumulative meta-analysis. So you can say, so by 2017, the evidence was really clear. So one was cumulative meta-analysis. Cumulative meta-analysis can tell you whether the point estimate is going this side or that side, what is the confidence interval of the point estimate. Recursive meta-analysis, cumulative meta-analysis, same kind of concept, but it will ask you, is the estimate stable or unstable? For example, if you looked at it here, it all seems to show towards harm, but this study suddenly shows, it may not be harm. So you can say at this point, it's not a very stable estimate. So recursive meta-analysis, cumulative meta-analysis talks about the stability of this cumulative data, but is it stable by here? So they need not have recruited all these patients, right? Remember, these all patients, one arm got the harmful stent and they might have died. So this is recursive. Then the other one which I did, exit meta-analysis, I couldn't find any example. Exit meta-analysis is exactly the word. It comes from the concept of research waste. Technically, one could say that this is waste, like these all studies should not have been done. Time, money, patient's life. So they say, at what point should the meta-analysis stop? Please do not do any more studies. So the Joanna Briggs Institute has come out with the guidelines, exit meta-analysis. At this point, we must tell the world, please exit, not from doing meta-analysis, exit from doing any more primary studies. We have enough information, either to say it's good, it's bad, or it doesn't work. So that's the concept of a exit meta-analysis. Okay. So now the guidance document. Guidance means, yeah. Yes, but their focus of the exit strategy is to tell you at the end of this should we stop or don't stop. I mean, it's all the same thing in different words, but basically exit meta-analysis is the concept that we should exit from doing any more studies. It's just the same thing in another word, but their focus is to say we call it exit meta-analysis. Now, so far I told you about results for significant meta-analysis. I told you 3 different methods. One is called the fail-safe number. Remember that file drawer problem and the fail-safe number. Anybody has a doubt in that? I mean, it's a concept. You just have to understand that, hey, there may be many studies which are negative. The results are positive. How many negative studies should I add to change the results from being positive towards null or negative? The second one is Bayesian methods. We don't have time to go into Bayesian methods, but basically Bayesian methods, there is some prior information. We have the information from the current meta-analysis. If you combine the prior information from the current meta-analysis, we come to some new data which is called in Bayesian as posterior information. We are not only just looking at the current meta-analysis, we are trying to combine prior data or prior knowledge. Prior knowledge plus the current data gives you a newer, better information called posterior knowledge. That is the Bayesian concept. The basic problem when you have meta-analysis or multiple data is the problem of type 1 error. Type 1 error is falsely concluding that the treatment works or is better. If you are doing a single study, it is called false positive probability. If you are doing multiple studies, it is called false discovery probability. Can you tell me some studies where false discovery is very high? Offline, online, anybody? Genetic tests, we have some thousands of genes and we are comparing human beings with disease, without disease, and you are doing like not only one gene, you are doing 1000 genes per person into 500 people and then comparing 2 groups, very high chance of getting alpha error. So, you may even get out of 1000 tests, you may get 500 false positive results. So, how to limit the false positive in that is called this false discovery probability, limiting in multiple experiments. In frequentists, there is a technique called Benjamini-Hochberg procedure. It's nice to read if you're interested into that. But we can use a Bayesian concept into that, false discovery. When you do large number of experiments, chance of type 1 is going to go up and up. How to limit that is called the false discovery probability. So, these are the guidance. I told you different methods for mathematical methods for conclusivity. Now, I am going to tell you when to use, and I told you that for significant results, we can use fail-safe number and Bayesian. If the systematic review results are not significant, meaning we cannot conclude that A is better than B, then what do we do? What methods do we do? The methods, there are 3 methods which are recommended. One is called Barrowman's N method, which is very similar to the fail-safe method, slight variation. You just need to do some simple maths. I gave you that example. Did you have to do any maths to do the example to file the number of the fragility index? No, just add 1 and what happened to that? That's it, finished. Similar to that is Barrowman's method. Conditional power method also can be used for non-significant meta-analysis, and R is a software which can help you with that. Simulation based methods are more complex. I told you the picture of simulation. Obviously, you have to have some knowledge of how to do simulation. There is no simple R or software which will say do simulation and tell me. So, it is multi-step iterative process. You keep on trying one, then it does not work, you try another one, you keep on trying till you find some answer, iterative process. So, that simulation based method is little more complex, but these are the 3 methods which are recommended for non-significant meta-analysis. Fail-safe number and Bayesian methods are recommended for significant meta-analysis. Okay. Then suppose I say I don't want to make this, I can choose any method I like. Fragility index, extended plot, cumulative meta-analysis can be used for either. These are methods which are common to both significant as well as non-significant meta-analysis. I told you about fragility index, robustness of meta-analysis, number of participants to be added to change the results, not of one study but the whole meta-analysis. The whole meta-analysis, if I just add one patient to one arm, suddenly the whole result changes. That is fragility index. There is an online tool for fragility index of meta-analysis. R packages are also available for fragility index. Extended funnel plot, there is a Stata package. Stata is a software for analysis. Some people like to do extended funnel plots. Some people find the whole funnel plot confusing. Cumulative meta-analysis, also there are software available to do that. Okay, so till now I talked about meta-analysis. Now I am going to talk about mathematical methods for sequential analysis. So this is called cumulative meta-analysis methods. There are two special methods for cumulative meta-analysis. I showed you cumulative meta-analysis, that example of that stent, that's called cumulative meta-analysis. Previously I showed you one for the jaw surgeries and how the effects didn't change, but the confidence interval became wide and the estimate came closer to 1. One is called trial sequential analysis. This is for cumulative meta-analysis. Another one is called sequential meta-analysis. There is a small difference between the two. Very often people think that, oh, these are same, I did some TSA method. This is a very nice website for anybody interested to learn about trial sequential meta TSA. It's ctu.dk.tsa, a very nice website to learn these things. So I am going to just teach you the concept of trial sequential analysis in an individual study. I think Reba talked about this. You talked about it, or somebody else talked about it on Saturday? Anna talked about it? Had a trial sequential analysis. Okay. So I may just take you all slowly through this because I like this, so it may not interest everybody. On the x-axis is time. At time 0, how many patients are recruited? 0. As time goes on, patients are increasingly recruited. On the y-axis, this favors intervention, this favors placebo. You can think of this as a relative of a risk difference of 0, but usually they put the Z score, which is a little statistical, but we don't have to worry about it. Basically think that if the dots go above, intervention is doing better, dots go below, placebo is doing better or harm. You can think of these dots as individual patients or in a systematic review, individual studies. So traditionally we will put this as p.05. This is the p value 0.05 for benefit and this is the p05 for harm. But when you are doing one study, it did not cross that. When you are doing a second study, the cumulative meta-analysis crossed that threshold. So we may say stop, but that is a mistake. So this in medicine is, if you had done one more study, it will come down. You know what that concept is called? Regression to the mean, null. Null is there is no difference. So the null hypothesis is always that there is no difference between two arms of a study. So you should never stop early. So if you stop early, you will make a alpha error. So instead of keeping this here, what this trial sequential analysis says, oh, only you can't stop here, only after the fourth study, if that estimate cross this boundary, then you can stop. As you collect more and more studies or more and more patients, you are a little bit more lenient with the stopping boundaries. There is a stopping boundary for benefit, there is a stopping boundary for harm. And at a midpoint you can decide, hey, should I stop here for what? The point estimate is here for no effect. This is futility. Hey, I came halfway, I didn't find anything. Might as well save my money and time and stop and put up my hands and say, okay, surrender, we cannot do any more. So trial sequential analysis principle can be used in a large randomized controlled trial. It can also be used in meta-analysis. So this is just explaining that in an RCT format. Now we learnt about required information size in a single study, that is a sample size. In systematic review we call it optimum information. It's simply that somebody didn't want to use sample size, optimum information size. This is the usual the boundary of 0.05 and this is the stopping rule we have here. This is one study just came there, second study just came there, but the third study crossed the TSA or the trial sequential analysis boundary. So that's the way this particular, and this is a nice article about in Cochrane reviews which were non-significant. How many did the TSA analysis say that we can add some more or don't stop. So this is the concept of trial sequential analysis. So we are really worried about this top part. I didn't show you the bottom half because we are really looking at falsely concluding that the new drug is good. So that's the type 1 error that we are really worried about. So we are really interested in TSA on limiting type 1 error. So type 2 error is the bottom half. Now I told you that there are two things that's quite slightly different. Trial sequential analysis, slightly different from sequential meta-analysis. It's all just the word trial is different. The only thing is the stopping rules. Remember those two boundaries I told you above and below. In sequential meta-analysis there is something called triangular boundaries. In this analysis we did not include heterogeneity, but systematic review has another thing called heterogeneity. So sequential meta-analysis includes heterogeneity, and it's a sort of a Bayesian framework. For TSA, that website which I showed you earlier, there is a nice software available to do trial sequential analysis. For sequential analysis, there is no software, sorry, you will have to do some sort of your own methodology to try and improve this existing method. So at least this is till March 2026. Now, this slide should have been deleted, but there are some other methodologies which I will just skip this slide, which I am just going to mention because some people will say that, did you hear about these methods? One is called law of iterated logarithm method, another is called fail-safe K method, the third is called Schuster-Pocock or Schuster-Pocock method. So the law of iterative logarithm, because you are doing repeated testing, which error increases? Type 1. So how do you penalize for that? We want to prevent that by using logarithm in that. Fail-safe K method, it is a rule of thumb. The maximum possible number of hypothesis tests before type 1 error exceeds a pre-specified threshold. We are teaching the Ulta in Saturday sessions. If you have 5 subgroups, we divide the P05 by 5, and that is called Bonferroni. This is a Ulta like. After how many groups are you going to cross one threshold of P value which you should not cross? That is called the fail-safe K. So the Schuster-Pocock or Schuster-Pocock, I think I am murdering the pronunciation. It adjusts based on the desired P value, number of tests and the number of studies. So it's slightly more complicated than fail-safe K. None of these newer methods has any dedicated software. I don't know. There are some other methods which I can't show you here. One is called quality control methods, but it's something somebody can read. Now, in the world of AI, everybody says, what is this nonsense? You are teaching all these techniques. Just ask the AI, ChatGPT, should we do more studies or not? So that is prediction and machine learning tools. It looks at the overall conclusion rather than P value. What is the likelihood that a new study will come along which will change the conclusion given the current evidence? The new study should be so big and so narrow confidence interval. And when was the last search done? Hey, the last search was done 10 years ago. Then there is a high likelihood that there is another study which was there which you should have done to update your meta-analysis. So in the traditional method so far, they don't look at when did you last search. Like for example, Anna did a review and then we said, okay, our search is a bit old, we have to do another one. This machine learning model would have told you, Anna, better search again because your search has been a bit old. So it looks at some more things and it's a bit challenging to implement. You can't ask the ChatGPT, how did you come up with the suggestion that I must do one more search? It will just tell you have to do or not do. So that methodology understanding is a little bit of a black box, meaning I don't understand how the machine learning came up with that. So there are 3 types of machine learning. One is called prediction model, another is the CART, and the third is machine learning, which is random forest, decision tree and regression classifier. Now they are all telling you the same thing, whether the meta-analysis should be updated. And the prediction model looks at 2 things, logistic regression, which is what we are used to. We all know logistic regression, and a qualitative decision tree. Decision tree is like if you do, will you get more? If you don't do, will you get more? This CART is called classification and regression tree. One day maybe we can take a Saturday section on CART. It looks at 3 things, time since the last search, number of studies which you have included so far, and the number of participants included so far. It also looks at something called the coverage score. I'll talk about coverage score. The same things are done by this another technique which uses machine learning, which is another machine learning technique, which is random forest or decision tree or regression classifier. So it's just three different subheadings under machine learning methodology. What is this coverage score? Coverage score, you divide the number of participants before updating by the number of participants after potentially updating. That gives you a number called coverage score. I mean, it all sounds like Greek and Latin, but it's good to know these words because increasingly everybody is relying on systematic reviews to make guidelines, and guideline developers are asking, is the systematic review evidence conclusive? And people don't want to do mathematics, they'll increasingly turn to AI, and the AI will give you something called coverage score, and you should not wonder what is this coverage score. Now I'm going to the easier part of the talk, which is a little more relaxed to do, grade, and you all know grade. And then now I think Anna did this diagnostic test evidence. Did you talk about grade in diagnosis? Briefly. So there's grade for intervention studies, now there's grade for diagnostic test. I think there are about 45 or 50 grade varieties, and now there are grade for prognosis studies, grade for everything. What Reba talked is core grade for systematic of intervention study. So if somebody is interested, you can go and see our video on core grade. Now, as I told you that if you do grade, I'll make an alternative to grade. You know, it's like everybody wants to put their name to something. So there are various other things. There's something called Agency for Healthcare Research Quality, AHRQ, Evidence-Based Practice Center Methodology. Then there's a same thing for intervention studies and for diagnostic studies. Then for Research Gap Framework, US Department of Agriculture Framework. Like that, there are many. All these are really something similar to grade, same questions put in different orders and called differently. For toxicology, I'm sure the medicine one will be interested in this National Toxicology Program Framework for Evidence. Network meta-analysis, I don't know which of you took network meta-analysis. One of you taught. Did you teach cinema? You use the cinema framework. So it's the same thing, grade in network meta-analysis. People won't like me saying that, but it's basically grade in network meta-analysis is a fancy word called confidence in network meta-analysis, which we all like short forms, cinema. Okay, so then there are some more methods which come. Ottawa is from Canada, RAND method, Cochrane Review Updating Classification, ECRI based evidence rating system, and the European System of Cardiology. I don't know if you all seen cardiology guidelines, evidence level 1, 2, 3, in 1A, 1B, 1C. 1A will be high quality systematic review evidence, 1B will be like that. So they have decided to divide the evidence into various other qualities. Okay, does this look familiar to everybody? Okay, those of you who like grade, I just wanted to end with this because people think that, oh, grade is not useful at all. No, grade, you have to do grade as part of the story. After you look at the studies, the quality of the evidence, risk of bias, grade, I'm just urging that you also look at the conclusiveness of the evidence. But I'm ending with grade to show that people will think, okay, now we don't need grade anymore. And just remember that for grade, randomized studies start at high quality evidence, confidence of the estimated COE, and then if there are study limitations, we rate it down. If there are all the studies are all over the place, which is also called inconsistency, we rate it down. If the PICO is not exactly what we want, we rate it down for indirectness. If the confidence interval is crossing the minimum important difference, we say imprecision. If there is, what is this plot? Funnel plot. So obviously there are no studies on this side. Some people don't like the word publication bias. Now we use the word dissemination bias or some other bias. And I told you we can now do this extended funnel plot. And like we say nip and tuck in plastic surgery. You can trim and fill. You can add new studies to say what will happen to that. So these are the ways in which randomized control study evidence is downgraded. Non-randomized study, let us say we do a what study? Cohort study. It starts off at low, but if there is a dose response relationship, higher doses, more smoking causes more lung cancer. Rate up the evidence. Large effect, the odds ratio or relative risk for smoking is 20. Oh, smokers have 20 times higher risk of lung cancer. Then we'll rate it up. And then opposing residual confounding. So always in cohort studies, case control studies, we are always worried about confounding. And if these people have adjusted for confounding, or the confounding is going in the same direction as everything else, then you can rate up the quality of this. So in the end of it, we come to the resulting confidence, we say high, moderate, low or very low quality of evidence. So it's just all these are adaptations to the grade framework. So we should not get too worried about, and they're context specific. Toxicology group says, hey, we don't want to follow grade, we'll have our American toxicology evidence. Cardiology society says, we don't want to use grade, we'll use cardiology society grading. So don't worry about these too much. So anyway, I have told Ottawa is slightly different, RAND is slightly different. So we just take Ottawa, how they search for new evidence to determine if new systematic review is done. So what does Ottawa suggest? Initially you survey using through a limited search, you just search PubMed. And then if you say that there is nothing new, then you make a decision, should I do a more comprehensive search? Then you can detect quantitative signals, substantially smaller effects. The new studies are all less effective, it may reduce my confidence overall. That's called quantitative signal. That means the new studies are also showing benefit but less benefit. What is called a qualitative signal? The new study is showing opposite effects, or there's a new large study found in my quick search. Then I'll say that okay, there seems to be something out there, I better update my systematic review. This is all about updating a systematic review, not doing a systematic review. So this is called Ottawa rules. Similarly, the RAND. RAND is basically you ask the experts, Vignesh sir, should we do some more? No, I searched recently, I didn't find anything. Okay, that's it. No need to update the systematic review. That is a bit about RAND. I'm making a fun. I'm not making a fun, I'm making fun of that. Then there's a Cochrane review updating classification system. If anybody is interested, you can see how the Cochrane plans this. ECRI, EPC evidence rating system, ESC of the European System of Cardiology, they also have their own methodology for updating systematic reviews. Now I will just show you that somebody was interested in reverse fragility index. Remember, fragility index is the systematic review has found benefit. How many null studies should I add, or how much extra negative data should I add to make it inconclusive? Reverse fragility index is the systematic review found no benefit. How many patients or studies should I add to make it into a positive finding? So I will not take this in detail, though I have some slides on that. In the interest of time, I will not go into that. But just remember that it's an inverse logic. The number of events to change a non-significant result into a significant. That's the reverse fragility index. And if I divide that by the total sample size, I get something called fragility quotient. This is reverse fragility quotient. Okay. I'm not going to say anything about this, I'll just skip this, but this, when you want to know whether new studies should be added, we never talk about sample size heterogeneity, but you can also include heterogeneity into your sample size calculation to see whether new studies are required or not, because heterogeneity is an important part of sample size calculation. So let us summarize. Mathematical approaches means you have to do some additional math. File drawer is very simple. Take out one subject, add one subject. Some are simple, some require software, some require R which have extra packages, some require Stata which you may or may not have. The most important thing for cumulative meta-analysis, what we are really worried about is, if we keep on adding new studies, are we getting type 1 error going above that line which I showed you in the TSA picture. TSA software is available, but it's complex. Somebody must understand TSA to learn to do that. The second summary is that statistical significance is not equal to clinical significance. conclusiveness of a systematic review talks about clinical significance, not statistical significance. So you need to talk about the context. What was the quality of the risk of bias? What about heterogeneity? So we often avoid using the word this is conclusive or inconclusive. We make a more nuanced approach to the whole thing. We don't like the threshold of P05. So statistical inference is conditional on a specific hypothesis and assumptions. What are the assumptions in systematic review? Can I do a fixed effects or a random effects? If I choose odds ratio, I can use Peto method, Mantel-Hansel method, then inverse variance. So I can modify my methodology slightly to get a p-value of my choice. So one must be very careful while interpreting conclusiveness, significant, non-significant, knowing that there are so many mathematical or statistical things going into a systematic review before one says the evidence is conclusive or non-conclusive. So this means nuance. Nuance means little deeper understanding. What do most people say? The systematic review showed p value less than 0.05. Hey, everybody change your practice. That is not a nuanced opinion. What was the quality of the studies? What was the risk of bias? What is the grade? Did it reach the minimum clinically important difference? Was the odds ratio, fixed effect, random effects? Did they use the correct methodology for that? All that, and was the final review, have they looked at conclusiveness of the systematic review? All this together is called nuanced view. Okay. So to end where I started off, funders of guidelines will decide whether a new study is warranted based on conclusiveness. Systematic review authors will decide whether I should update my systematic review or end meta-analysis. Trial sequential analysis is an opportunity whether a new study is to be done or not done, or we should keep on adding new studies. Mathematical models which I talked so far is more on statistical significance, but guideline developers must look at a broader context before they make their guidelines. Non-mathematical approaches like grade don't require any statistical skill. So if you don't like maths, you can focus on that part. Systematic reviews are teamwork. You need content expert, methodology expert, somebody, patient group, health economist, qualitative scientist before you can convert a review into a guideline. So you may say that I am not interested in statistical part, I am only going to focus on the grade. Statistician may say, look, I will focus on meta-analysis part, I will also tell you about conclusiveness of the systematic review. So rather than, what all I talked today is to try to tell you that rather than saying that systematic review conclusively said this or that, there is some mathematics behind saying the word conclusiveness or inconclusiveness. And the grade framework is widely used by people everywhere. So research waste means unnecessarily doing research. If the evidence is already conclusive, don't do another one. That's research waste. So I will end here with this part. I know it's been a bit of a new kind of topic. For me also it was a bit new, so my slides might have been all over the place a bit. Apologies for that. Are there any questions from the online audience?